Now, a really familiar example of this is the way in which yellow light can be simulated by combining red and green light. So I'm sure you're all familiar with these kind of things. You've probably seen them at school or in science museums. You take a torch with a green filter and a torch with a red filter, and then you shine the beams so they overlap, and where they overlap you get yellow. And you can do the same with blue, and where the three of them overlap you get white. Now, I don't know about you, but when I was introduced to this idea at school, I certainly took away the idea that this was a property of light. This was telling me something about how light is. And I believe that is what scientists used to think, but it's not the case. It's actually telling us something about our visual system, not a property of physics at all. It's a property of human biology. So let's go through and see in a bit more detail how these metamers work. Okay, so let's imagine we've got some yellow light and it's monochromatic. So by that I mean a spectrum that consists of just one single wavelength. So the spectrum would be 0, 0, 0 and then have a big peak at this yellow kind of wavelength, so about 580 nanometers, something like that. And let's say, for the sake of argument, that at that position, light of that wavelength activates the M cone by 0.6 of its maximum and the L cone 0.95 of its maximum. It doesn't activate the S cone at all. So the LMS value for this light is 0.95, 0.6, 0. Okay, and we perceive that as yellow. Now let's consider a different situation. So now there's no yellow light at all. There's simply some monochromatic green light and also some monochromatic red light. So some light that's got a wavelength of 520, 530ish, and some that's got a wavelength of 660, let's say. Now this green light, I've positioned it so it's right at the peak of the M cone sensitivity. So you would think it would activate the M cone maximally, and it does, but I'm just going to turn down the brightness of this green light by a factor of 0.6, so that overall the total activation of the M cone by this green light is 0.6. And the M cone doesn't see the red light because I've positioned this red light, let's say, just off the end of this, so we can ignore any response of the M cone there. So the M cone is going to respond with a value of 0.6, its maximum activation, to this combination of red and green light. Okay, now let's go through and think what happens for the L cone. So the L cone can see both these lights. It can see it's activated by the green light. So the green light is just a little bit below its peak sensitivity. Let's say it's at 0.9 of the maximum of the L curve. And remember, the light has got a brightness of 0.6. So multiplying those two values together, we can see that the L cone is being activated by 0.6 times 0.9 by this green light. It's also activated by the red light. Now the red light is at a wavelength where the L cone is much less sensitive. Let's say it's at 0.1 of its maximum sensitivity. But I've really turned the brightness up of this red light. It's got a value of 4.1, let's say. So the L cone is also activated by 0.1 times 4.1. And if you type those numbers into your calculator, you'll see that they're 0.95. Now, that's not an accident. You'll remember that 0.6 and 0.95 were the M and L cone activations caused by the yellow light. So in other words, the monochromatic yellow light and the green plus red light are causing the exact same cone activations, 0.6 M, 0.95 L, and nothing of the S cone. So your brain has no way of telling which of these two possibilities is on your retina. Are you receiving only photons of 560 nanometers, or are you receiving a mixture of photons, some at 530 and some at 660? You just can't tell because your retina would respond equally to both of those. So even though they're physically different, and you could discriminate between these with a piece of physics equipment called a spectrophotometer, or with a diffraction grating, or anything really that would enable you to separate the wavelengths, perceptually these lights are indistinguishable, and that's exactly what a metamer is. And the point to bear in mind here is that always in perception, any information like this that is lost at the initial encoding can never be subsequently recovered. At best, the brain can kind of guess about what's most likely to be out there, but fundamentally that information is gone. Because humans have 3 cone types, we're said to have trichromatic vision, so 3-colour vision. And that has important implications for people making visual displays. For example, your TV screen, your phone screen, everything only has to have 3 colour primaries. So almost all displays just have pixels that are made up of blue or green or red in a particular pattern. And by activating those at different amounts, they can simulate a whole range of colours. And you can see oranges and purples and pinks and all sorts just from these mixtures of blue, green and red. Because we only have 3 cone types, you only need 3 pixel types in order to be able to reproduce the complete range of colours that we have in the real world. Now, I mentioned that this is just a property of humans, and that's really brought home when we consider other species. So it's by no means the case that all animals are trichromatic. Some have got worse colour vision than us. They can be dichromats or monochromats. Many animals have better colour vision than us. So this estrilded finch is a bird that's tetrachromatic. So it actually has 4 classes of photoreceptor. It can, as well as an S, an M and an L cone, somewhat different from our own. As you can see, they're spread more evenly over the electromagnetic spectrum. It also has this sensor which enables it to see in the ultraviolet. So this bird can see colours that we just can never imagine. And that's impressive enough, but wait till you see the peacock mantis shrimp. So this amazing creature has actually got 12 different classes of photoreceptor with different spectral sensitivities. So it's got dodecachromatic vision. And there's a lot of speculation, of course, about exactly what this animal can see, how the world appears to it. So given the number of cone types that a creature has, either 3 or 12 as in the mantis shrimp, how do we read those out to produce information about the spectral content of light? Back in the 19th century, there was a long controversy between Hermann von Helmholtz on the left here and Ewald Hering. Helmholtz followed Thomas Young and was convinced that there was a lot of evidence that human colour vision depended on 3 basic primaries, red, green and blue. And he worked that out purely from behavioural evidence. At that time, nobody knew about the cones and rods in the retina. I mean, they could see the cells there, but they had no idea that there were 3 kinds of cone types. That was only found in the 1960s. So Helmholtz was deducing the existence of the 3 cone types and actually got their spectral sensitivities fairly accurately, but purely on behavioural evidence about what people could see. But Ewald Hering, on the other hand, said, no, you've got it all wrong. The thing here isn't about 3, but 2. There are 2 colour axes, clearly. There's a red-green axis and a yellow to blue axis, and that's the best way of describing our colour vision. And as so often happens in these kind of controversies, I guess, they were in fact both right in a way I'm going to explain now. So given these 3 cone types that we have, our visual system combined them so as to extract essentially 3 different channels, 3 ways of getting information about the visual world. One is simply luminance, and you can think of that as the sum of all the cone activations. It's very much dominated by L and M, but in principle it's like the total activity in all the cone types. Then you have a red-green channel, so just like Hering suggested, which is made up of the ratio of the cone activations in the L type to the M type. So think of the balance between L and M, and that's your red-green channel. And then we also have a blue-yellow channel, which is the ratio of S to the sum of L plus M cone activations. And so you can see although Helmholtz was completely right that we have these three cone types, Herring was right that they are combined in a way as to give us two colour channels, one red-green and one blue-yellow. In terms of genetics, the DNA sequence that encodes the L and M cone pigments are virtually identical, and that suggests that they actually evolved from a single pigment fairly recently in evolution, and so that's why the L and the M cone spectral sensitivities are so similar. That's the theory anyway, that they simply haven't had the time they need to evolve further apart. Whereas the S cone, it seems clear it's separate, it's on a different chromosome, and it seems to have evolved much earlier in evolution. So that means early on we can only have had what is now the yellow-blue chromatic channel. So our visual system would have evolved to compare information in the S cone class with that in the other cone class. I'll call it LM, because that distinction between L and M would not have evolved back then. And then more recently, when L and M split apart and became spectrally distinct, our brains discovered it was useful to compare the activity in these separate cone classes separately, and we evolved this more recent red-green colour channel. And then also, if you simply sum all of them together, then you have this luminance channel, which is sometimes called the achromatic channel, because of course you're losing the colour information there. Now, you've probably seen these kind of after images which rather nicely demonstrate the opponency between blue and yellow and red and green, just like Herring had argued for. So this is an image prepared by my colleague Anja Hurlbert. It's of Dunstanburgh Castle, just up on the northeast coast, about an hour north of Newcastle. If you look at the spot there, just rest your eyes on that spot and just let your retina adapt to these colours. You see some very bright blues there, orange sky, kind of purple ground. So look at that, and then I'm going to flip to the next image, and I don't know about you, but I see it in beautiful colour. As soon as you move your eyes, it's spoiled, but if you just keep your eyes where they were, then you see really compelling, convincing colour in this, what is clearly in fact a monochromatic black and white photograph. So what's going on there, you might like to think through. It's an after effect, very much like the tilt after effect that we discussed a couple of lectures ago. So let's go through that, just as we did with the tilt after effect. Normally when you look at something grey, it causes equal activation in the blue and yellow channels. How much activation determines whether you perceive it as dark grey or black or light grey or white, but the balance should be equal. And that's why you perceive this stimulus as grey. Now when you look at something blue like this, obviously that activates the blue channel much more, and there's an imbalance and you perceive the object as blue. And then the point is, when you go back to looking at the grey after having adapted to blue for a while, then there's much less blue activation than would ordinarily be caused by this grey stimulus, and so there's an imbalance, and now more activation is found in the yellow channel, and so your brain interprets that as indicating that the scene you're looking at is yellow. And that's thought to be very roughly the kind of neural basis for these sort of colour after effects.